In this video, we'll talk about how the inverse trigonometric functions are defined. We've already spent some time talking about inverse sine, inverse cosine. The basic idea is they're the angle for which the sine or cosine equals a certain number. They're basically defined by the relation that y equals, say, cosine inverse of x if cosine of y equals x, the basic idea for inverse functions. The only thing that's tricky with these is the domain in which they're defined. So for cosine, we say that this y value will be between 0 and pi, which makes sense if you look at the graph of the cosine function. One sort of stretch from 0 to pi covers all the values cosine could take on. So to get a well-defined function, I have to say that my output value is going to be somewhere between 0 and pi to give me a single unique value that is the inverse cosine of a number I put in x. Similarly for sine, this will be between minus pi over 2 and pi over 2. For the same reason, that gives me one covering of the functions, so that every value has one unique output through this inverse function. We can do the same for the other trigonometric functions. Again, getting the angle that corresponds to a given tangent or cotangent output. And the important thing again here is where the output values will be for these functions. What value I'm going to get for inverse tangent, and where does it live? So again, we basically have that y equals, say, inverse tangent of x if tangent of y equals x, and y is in the interval from minus pi over 2 to pi over 2. If you think of the graph of tangent, that gives you one of the swoop curves of the tangent function. If I take one of those, that will give me one covering everything and give me a unique value that defines as the inverse function. Similarly, y is cotangent inverse if cotangent of y equals x, and y is in the interval from 0 to pi. Again, in terms of cotangent, that covers one curve of the function, and so that gives us a way to define this inverse function here as well. The other two are a little trickier. Y is secant inverse, again, if secant of y equals x. And the issue here is that the values you can put in for x here are not continuous for the secant function, because secant has to be bigger than 1 in absolute value. It can't be between minus 1 and 1, because 1 over that has to be a cosine, and that's going to be outside minus 1 where cosine can live. So, and y is in the interval from 0 to pi over 2, or pi over 2 up to pi. And here we see the issue of that, the fact that those values aren't contiguous with each other, the fact that I can't include pi over 2, right? Secant of pi over 2 is not defined because cosine of pi over 2 is 0. However, this is the same interval up to that pi over 2 in which we define the inverse cosine function. So it makes sense to think about it that way, but because I can't plug in pi over 2 to cosine 1 over that gives me 1 over 0, I just split this up. And the same here goes for cosecant. So y is cosecant inverse if cosecant of y equals x, and y is in the interval minus pi over 2 to 0, or 0 to pi over 2. For the same reasons as above, that's the same interval which we define the inverse sine function, having to exclude 0 because inverse sine of 0 is 0. And I can't flip that over to put that in the denominator. So that's how these inverse trig functions are generally defined, and we'll see in future videos how to go about differentiating them.